So thanks to the organizers for giving me the opportunity to talk about this hot topic. Indeed, I saw many other presentations touching upon the subject. And my aim is to add some remarks, let's say, on the subject and maybe thought-provoking questions. So this is an idea that I had at the end of my PhD in Milan with Matteo Paris, and then I continued in Laboratoire Castelbrossel with Carlos and Mattia. And our reason to study the topic, the position and momentum estimation, is rooted in a fundamental question about the role that non-Gaussian states can have in quantum estimation. Because typically, if you have just Gaussian states, you can crank up the energy, squeeze more, displace more, and this is usually okay to estimate single parameters. There seems to be very little cases in which you truly need non-Gaussianity. But the situation is less clear when we have multiple parameters and issues of quantum incompatibility. So what is quantum multi-parameter estimation? Okay, we suppose that we have this continuous family of parameters that are encoded in quantum states, and then we try to retrieve them, to retrieve the true value by applying a P of M, a measurement. And then from the M results of this measurement, we perform an estimator. And if this estimator is unbiased, we will find the Cramer-Rao bound, so the covariances, so the error essentially is lower bounded by 1 over m and also by the inverse of this Fisher information matrix, which is dependent on the probability distribution, hence on the measurement that I am doing. And for single parameters, one can maximize over the measurements. And the result is the so-called symmetric quantum Fisher information, and it can be computed starting from these L operators that are defined implicitly by these equations, the symmetric logarithmic derivatives. And this is indeed reached by some measurement, at least asymptotically. It can take a lot of measurements, but it is in principle possible to saturate this bound. Whereas for multiple parameters, the situation is radically different because one can define this symmetric Fisher information, but the maximization cannot be done in general for all the parameters at the same time, because one can have that the best measurement for one parameter is different from the best measurement for another parameter. So typically one fixes a positive matrix W, which gives weights to the various parameters, and then maximizes the trace of W times the inverse of the Fisher information over all possible measurements. And this is a W-dependent problem. And in this way, we get the maximal informative bound. And so in general, the symmetric Fisher information bound is not tight. So it's strictly less for most cases than the maximal informative bound, meaning that the error that we can attain is larger than we expect. So let me introduce two more bounds that will be useful in next. One is the Olevo bound. It has a quite involved expression, but basically one introduces these operators X that satisfy these constraints, and then minimizes this complicated expression over all X's. And this is the bound in error that one can, in principle, attain if you allow for correlated measurements on many copies of the state. So it's a bit unphysical. And for this reason, there is also the bound that you can have if you are only allowed to do sequential measurements. So on each copy of the state, you have to do the same measurement many times, but without correlations between the measurements. And this is the Nagaoka-Hayashi bound. So how they compare to, okay, so in particular, there is also this theorem, which is important, the following, that they are equal for pure state models. It's not a very famous, I mean, it's not very well known. Indeed, we have to discuss a lot to clear up this result. And so how they compare to the symmetric quantum Fisher information bound? Well, it's convenient to introduce this quantity, the Ullmann curvature, which is related to the commutator of the logarithmic derivatives. And it's actually the geometrical curvature of the statistical model. And by introducing this quantity, we can compute a parameter R. Okay, for two parameters, it's just the ratio of two determinants under square root. And this parameter is bounded between 0 and 1 and precisely gives us the difference essentially between the Olevo bound, so the one that we can achieve if we allow the most exotic measurement strategy, and the symmetric quantum Fisher information bound. Okay. So we want this R to be as small as possible, essentially for compatibility, or at least this is one of the conditions that we would like. So what is the problem that I will discuss? We consider a probe state that is displaced in both position and momentum, and it's a very well-known problem. I will consider, though, the joint estimation problem. So I want to have as high precision as possible in both parameters. Here are two of the most recent results on the subject, but in general, it has been studied using numbers, Fock states probes, or compass states, more famously, introduced by Zurek. But we can compute the quantum Fisher information analytically in several cases. In particular, if we have a Gaussian probe, there are very general formulas, and one gets a very intuitive result, perhaps well known. I mean, the quantum Fisher information goes like the inverse of the covariance matrix. It scales like the purity, so in general, it's convenient to get pure states. But the intuitive fact is that the broader the state, the less precise it is at estimating displacements. So this is, I would say, the very intuitive one. But then we can do the analytical calculation also for a generic pure state, also non-Gaussian. And what we find is that, okay, this is the expression for the quantum Fisher information. We have this omega here, which is the symplectic matrix. It is there just to exchange x and p, because x0 will be bounded by the variance of p and vice versa. But we don't have the inverse here. So the broader the state, the more precise it is, without any further condition, assuming that the quantum Fisher information is a good figure of merit. And since it's pure, it can be broad in all directions, it's phase space, only if it is non-Gaussian. Okay, so this is a very unintuitive result. So, by the way, they are compatible because on pure Gaussian states, we have this inversion formula. But let me compare them more closely. So the determinant in the Gaussian case is always smaller than 4, while for pure states is always larger than 4. So in general, this scales with purity, and this scales with non-Gaussianity, let's say. So just to give you the remarks on what we found from these observations, let us consider also the incompatibility, okay, so the Ullmann curvature, which is constant in the case of pure state models. So in principle, you would say we cannot estimate both at the same time because they never commute the symmetric logarithmic derivatives. But the R parameter scales with the determinant as well. So in principle, with high non-Gaussianity, they become asymptotically compatible. Whereas you can also scale the R parameter in the Gaussian case, but only at the expense of purity. And so in principle, it's not useful for metrology because you will have not very sensitive states. Okay, they are compatible, but they are not very sensitive. So what we found is that for the joint estimation problem, still Fock states are optimal, as was known for example, for phase randomized displacement probing. We get this unintuitive inequality. We can have a closed form for the quantum Fisher information in the case of generic mixture. And if we ask what type of non-Gaussianity is actually necessary in this context, we find that, well, quantum non-Gaussianity is not even necessary because you can use this kind of mixture and get a good quantum information without having problems of incompatibility. And Wigner negativity, it seemed to be sufficient, but actually there are some counterexamples that show that actually it's not even sufficient to guarantee some advantage. So a very classical type of non-Gaussianity is sufficient for this kind of advantage. So I conclude, okay, so this is attainable on pure states because precisely the Nagaoka-Hayashi bound is equal to the Olevo bound, so the theorem that I mentioned before. So I'll conclude just with some open questions that we would like to address in the future. In particular, I think that the most promising application of these results is in witnessing non-Gaussianity, in constructing witnesses of non-Gaussianity based on metrological advantage. Thank you.
Thank you very much.
Thank you for a very nice talk. You said you will be provoking, and you really did. Yes. The point is, yes, I should repeat my previous argument. Fisher information is not enough. But here, in your case, you have a nice, I would say, benchmark. The problem is 2 parameters you wanted to estimate, can be measured. It's exactly what is in this whole level, actually started by Hellstrom. It is these projections into this coherent state or squeeze state as you want. So it means there is something like golden rule really in this metrology. If you can something measure, please measure, don't estimate. And if you estimate, then you should really count very well your resources. And it's clearly seen where these problems appear. The non-Gaussianity is nuisance because you cannot trust to this measurement, you must accumulate all of them. And in the end, you will create something like standard measurement by very expensive way, yes? Because you spend much more resources to get something like the result. Because there is this, and in your case, you can really check it somehow with the benchmark. Of course, it wouldn't be easy. If you choose your state, which is not, the state in which you measure the things, the coherent, I like that. But this is included in all this, let's say, developed theory. So please answer to my objection.
Yes, sure. So I think that there are two kinds of answer that we can give to this very legit observation. One is that there are some cases in which this advantage has been used. For example, Matteo Fadel was mentioning yesterday the possibility of detecting the non-Gaussianity in a certain sense. But I totally understand the point between the estimation and the measurement and the difference between the two. So this is totally, so the estimator that you would want to define, the saturability of the quantum Cramer-Rao inequality and all this stuff, totally they are relevant. In fact, I'm not claiming that this is the best technique to measure position and momentum jointly in a realistic scenario. At most, it could be convenient to probe non-Gaussianity. Okay, this sense. Yes, sure.
Do we have more questions? If not, then let's thank Massimo again.